Welcome everyone again for this afternoon session. So I'm Aymeric Blot. I will present for the next hour on a framework to do genetic improvement, to do automated software performance. The framework is named Magpie. And the slides are online if you want to follow along or have a terminal open to play with Magpie while I present it. The link will disappear, but if you Google my name, you will be able to find a link to the slides if you want to have them to follow along. So very quickly, I will introduce a little bit who am I and why am I giving this talk. I will talk about a little bit about Magpie. Then I will have three main parts in my tutorial. The first one, thinking Magpie, which will be slightly more on the theory of what is automated software improvement in the lens of Magpie. Then the second one, building Magpie, which will be more on the software itself. On the third one, using Magpie will be more the tutorial part, the hands-on part, when I will try to show you how it works and how to use it in practice. And I will finish with future directions and challenges. So who am I? I am Aymeric Blot. I am a lecturer in France at the Université de Rennes. I am a research fellow at IRISA, which is the largest computer science center in France. And I am a member of the diverse team, which is a joint team between INRIA and IRISA. So INRIA is the French Institute for Computer Science. I'm giving this talk because I am the main developer of Magpie. And before that, I worked on Piggy, which is another Python framework to do genetic improvement. And before that, still, I developed MOParam-ILS, which is a framework to do parameter configuration, algorithm configuration. So this is where I came from. Very, very quickly, we are in the genetic improvement workshop. But what is genetic improvement? It's, to put it bluntly, you have a software, you do stuff on it, and you get a different software, slightly better, slightly improved. The part genetic in the GI name comes from the meta-evolution process that comes initially from genetic programming, so genetic improvement. So on how we do the transformation, and GI has two main targets. One's improving functional properties. So for example, as the keynote this morning was for automated testing, doing stuff to a software to improve it. And the other core target is the improvement of non-functional properties, such as execution time, energy or memory usage, solution quality, security, a lot of it. We do have a website with, for example, a living survey on it. It's really great. Yeah, there is a lot of paper related to genetic improvement on it. The living survey is based on the bibliography from Bill, which is in the room. So if you have a relevant paper, the best way to contact Bill and to add it on the GP bib, and it will appear automatically on our website. So that was genetic improvement of software, but then what is software? And I don't really have a very good answer. I think to me, the best answer would be perhaps a description of something which is ultimately executable. So software can be a lot of things. It can be source code. It can be an artifact. So for example, you could say my software is not the C code that I wrote, but it's the executable that I have. And if I change something on the executable, that's a variant of my software. And there are a lot of points on which you can try to play. You can try to play on the initial design. For example, if you have an UML diagram, you can try to do transformation of the UML diagram and say that I have improved my software because I changed the way the classes are organized. You can apply automated transformation on the source code. You can apply on the binary. You can change stuff at runtime, for runtime, before the execution or during the execution. Software is kind of complex, but in a way, optimization can happen everywhere. And one of the observation issue is that most of the tools are really dedicated to one specific use case. You have tools that can take source code or improve source code. You have tools that can take UML and improve UML. You have tools that do parameter tuning. So that takes parameters that improve the value for parameters, but not really tools that can do automatic improvement of software as a whole at multiple points, because the process of improving is very similar on all of these points. So this is where I introduced Magpie. Magpie is a backronym for a slightly hard to say sentence, which is Machine Automatic General Performance Improvement of Evolution of Software. It's not really the point. The point is Magpie is a framework that is written in Python, so it's easy to install, easy to read and to use. It's a framework that takes software and model it. From that model, it will automate a search with transformation to improve that model and ultimately have improved software variants. I will come back later on the key points, but the key point is it's free, as in free beer. It's open source on GitHub. I try to keep it as small as possible, but to include many things, many features on it. And yeah, it can be used not as for a single use case only, but it is designed to be generic and trustworthy. It's for reproducibility. It is designed in a way that you can design experiments and repeat experiments easily. Brief history. I mentioned that I was working on Piggy before, which is another Python framework. Magpie is based on Piggy. Piggy was first introduced in the Korean Software Conference in 2017, presented in the ICSE workshop in 2018. I worked on the version 2.0 of Piggy in 2019, and then we added more and more stuff. So initially it was to work on lines of code on IST. With Piggy 2.0, we added support for IST through XML. Then around 2021, we added support to handle more than one single hard-coded local search. And then we introduced more about, I think the paper on 2022 was to do algorithm configuration. And then the more times pass on, the more I was rewriting stuff, reorganizing stuff. So the less and less it was looking like Piggy, and nowadays continue to work on the code and to introduce new features, and still trying to keep everything clean and simple. So this is the framework I will talk about. So the first part is more grounded on theory, then on the framework itself, and then the tutorial part. So we'll talk about the search space of GI or automated search process through the lens of Magpie, and then how in general the search process works and why does it work. So if you look at the big picture, what we want to do is program synthesis. At the end of the day, we want to write new software. We are not doing that from scratch. If you do program synthesis from scratch, you start from nothing, and stuff happens, and at the end of the day, you have new software. And that kind of hard, because the search space for that is the space of all possible software that you can write. It has a very natural representation. It's just software. So you can see that, for example, as monkey writing on a typewriter. So on a letter-by-letter basis, you can see that as words in a file. You can see that, for example, as a grammar. You have a grammar of how to write software, and you want to have the best realization of that grammar for one specific purpose. But it's kind of hard because, yeah, as I said, the search space includes everything, and you don't want everything. You want one software which is very good for your use case. It is hard to navigate because The syntax and the semantic is not the relation between syntax and semantics is not that clear. You know what you want, you don't fully know how to write it. The space is sparse. There are a lot of software and very few that does the one thing you want. But the good thing is it's very expressive. You can do everywhere just synthesizing software. But you start from nothing, and your software, the software you want is usually not that small. And the further away from the empty software, then the harder it is to synthesize programs. So usually program cities from scratch is either a one-shot if you use LLMs. I will try not to use the word AI too much in the presentation, or a clever way to do enumeration close to the origin, but it's hard. Genetic improvements does not start from nothing, but start from an existing software. It's basically the same search space, but instead of starting from the origin, you start from something that is already quite good. And GI comes with an ad hoc representation, which is a bespoke representation, which is a sequence of transformation. You start from one existing software, and then you will do some transformation to go from one software to a different software. The space is still virtually infinite. You could completely destroy your software and recreate one from scratch. It's still hard to navigate because you still have the issue that you know what you want, but you do not know how to write the software that do what you want. It's a little less expressive because you are basically looking at a subspace that is around your starting software. But in the other way to see that is you are centered on all the interesting variants, all the interesting software, which are the variants of the original one. If there is a software which is better than the one you already have, the hypothesis is it is kind of close to the original in that space, so that makes the sequence of transformation representation make sense. In particular for Magpie, the framework is really centers on the way you first model your software and then apply transformation. So basically, from a very, very large, broad lens, you start from your software, you then abstract it, so you have something to apply transformation on. You then start from an empty list of transformation, and then you have a main loop on which you will add more and more transformation. And from that list of transformation, you can recreate a new variant, apply it on disk, compute the fitness to see whether your new software is more interesting or less interesting, and then ultimately get your improved software. A few words on terminology, on internal terminology in Magpie or in the rest of this presentation. I will try to call variant a collection of model on which to apply patches. So that was the middle layer in this graph. A collection of model is an internal representation of a part of a target software. For example, a file. If you have main.c, it's your file. The model could be a list of the line in the file main.c. It could be the IST of your file main.c. It could be something else. Your variant is just a list of the model you use to represent your software. A patch will be a sequence of edits, and one edit will be a single model transformation. So going back to that, you start from an empty list of transformation, and you will try to find the sequence of transformation to apply to your original software to get to your improved software. With a slightly better lenses on the general search process in Magpie. So you start from your existing software, you then abstract part on which to focus. You might have a very large software and you might not want to evolve everything at once. So there will be part that you will left untouched on part that will modelize. that will model. And from those parts only, you will evolve a patch that will consist in trying to add or remove edits, so transformation to apply. Then from your new patch, you will apply all the transformation, create a new variant for which you can evaluate the fitness to see whether or not your new variant is more interesting or less interesting. And you will evolve that to get a larger and larger patch, better and better variants until the search ends and you can realize your transformation and get your improved software at the end. There is one arrow at the top, which is you might want to do more than one search. So this is the main search for which you start from an empty patch and you want to get a patch to get to a better software. You might want, for example, to test for generalization, to do a second search with a different fitness function, for example, using a different benchmark to make sure that what you learned during the first search generalize. You might want to minimize patch size, in which case you have a search from which you start from an existing patch and you want to minimize the size of the patch so that, for example, the diff is easier to understand, does not include anything that has no impact on the fitness, and ultimately, so that your patch is more easily accepted and merged into, for example, a Git repository. Last optional additional steps, you may want to actually look at the transformation to make sure that, yeah, you actually learn something interesting and not simply noise. And from all of that, Magpie will expect the user to provide the software to improve, of course, and basically either or both a test suite and an evaluation benchmark, something to on which to compute the fitness. Magpie will expect the user to specify which model to use, which search process to use, which are the available transformation to apply on the model, and a performance indicator to compute the fitness of the variant. Everything else, the procedure, the framework, basically, it's just automated through Magpie. The question then is, why does this kind of search work? And I have three answers to that. The first answer came from mutation testing, from which they have an hypothesis that they call the competent programmer, which is that competent programmers write programs that are almost correct. So that means that instead of starting from scratch to do program synthesis, we can indeed start from the existing software because it's a good heuristic as to where to search to find a better one. From automatic program repair, they have a new hypothesis, which is the plastic surgery hypothesis, which is basically on the transformation you can apply on your software, which is both you can apply transformation to get a better software, and that those transformations can be efficiently found and exploited. From these two, I want to add one that is from myself, is that there are infinitely many equivalent software, and basically your whole search space, or at least locally, is fractal. That is, there are many duplication in your whole search space of the entire search space. Basically, if there is a good variant which is close to your original software, you can do a few transformations, many transformations, and it won't change that the variant that you are looking for, it's still close as in the original search space. So basically, if you have a software, you can, for example, add int x equals 0, and it won't change the fact that you can correct a bug elsewhere. It's a transformation that has no impact on the search space. So you can start to explore things, and it won't really decrease, it won't increase the distance to your optimal. So you can apply neutral changes, you can apply neutral mutations, and keep the property that the software you are looking for still exists and is still closed.
Your questions during.
I am very happy to answer questions during the talk, and especially during the tutorial part, more hands-on part. I will be very happy to answer questions.
So hopefully this is going to work. Why would you describe this as a fractal?
So the fractal property is you have your, so the question from Bill was, why is it fractal and why I'm using that word? And so the fractal property is your object is repeated at a smaller scale inside your object. So if you look at Mandelbrot, which is a well-known fractal, you can zoom in and still find something which is very similar to the entire Mandelbrot fractal. If you have your core snowflake, you can zoom in and you have copies of the core snowflakes inside your core snowflake. For your search space in GI, so this one, you have your entire search space which is centered around your original software. And you can move around in this space, but most of the things you will see will be identical to the original search space. If you have one transformation from your original to the one that corrects your bug, you can move around your search space, do 1 move, 2 moves, 3 moves, 10 moves, and there are very high chances that the one transformation from your original to the improved one still exists many times in your software. So in that sense, your entire search space, you can have copies of it when you move around your search space. So basically everything, every time you do a transformation that has a very little impact, so you remove stuff that is not used, or you change something and it does not have a large impact, all the other transformations still exist and still can be applied to your new mutant in the exact same way that they could have been applied to the original one. So that's what I call fractal, in the sense that, yeah, you have your whole search space is still preserved when you move around. So you have smaller copies of your entire search space many times around your entire search space. So yeah, so that was for the theory part. I want to talk about a little bit more on terms of framework of Python on what are the components Magpie provides. And the last part will be more hands-on tutorial on how to use it. So Magpie in a nutshell. So it's still a Python framework. It is designed to be modular. It can be used to do genetic improvement, to do mutation testing, to do algorithm configuration, to do compiler optimization. It is designed in a way that it should be hack-friendly if you are a researcher. So if you want to add a new algorithm, if you want to add a new model, new types of transformation, you want, again, the LLM terms. If you want to introduce a new transformation that calls the LLM to, for example, use masking, then it should be easy to simply add that transformation and everything in the framework should still hold. And for developer, it should be user-friendly. You can, without any Python knowledge, you can use it to improve any kind of software. So the key point, so it is free as in free beer. It is licensed under MIT. The source code is online on GitHub. You are free to submit pull requests or inform me when you find a bug. That sometimes happens. It is very small size. If you count the lines of code, it's you get a number around 4,500. I recently listened a talk with Linux that said that 10,000 lines of code was readable in one sitting. So it's less than half of what Linux servers consider as readable in a single sitting. So it is small, but yeah, it provides many functionalities. And it is multi-purpose. You can use it to improve functional properties of software, non-functional properties of software. And trustworthy is it is because it is scenario-based. If you write your scenario, you will be able to repeat experiments in a very nice way. And that's something that I personally hold that's important, that you cannot really change much from the command line because it is important that your scenario file is written entirely and you cannot forget to repeat things that you might have only written on the command line. The question is, have I tried to run Magpie on Magpie? The next slide is a summary of the architecture. There is one example, one folder, which is examples. One of the subfolder is Magpie. So there is a scenario on which Magpie is applied to Magpie to improve Magpie. It's not the best thing in the world. You need to be careful about how you do it because basically running times can explode because you have one order of magnitude more slower than the times you need to run Magpie to see if your variant is more interesting or less interesting. But it can, yeah. Not probably in the way that you are thinking, but there is an example for Magpie on Magpie. So the source code is online on GitHub. You can download it now. What you will get is so this. I have a simplified version of it here. You will get some files that are not fully interesting. You will have 4 main folders. One is documentation, which is important. If you are writing software and do not know how to write documentation, I will very earthly recommend to look at ICSE, which is a way to format documentation. So in Magpie, you will have reference pages, tutorial pages, how-to pages, and so reference, tutorial, how-to. And explanations. But yeah, it's a really nice resource and something that I want to share. Don't be afraid of the .fr. It's written in English. You will have so a folder with many different examples. One of which we'll see in the next part, which is triangle C. There are many different examples, many different variants of triangle and minisat and Magpie, for which you will get the target software, and then in a subfolder underscore Magpie, you will get more files for example, scenarios that you can directly run, and we will run some later in the tutorial. The main part is a subfolder which is Magpie. So that's the folder which is 4,500 lines of code. You have the core of Magpie is Magpie core. That's 160 lines of code. And that's the one you need to, the one thing you would need to run in one sitting. That's all the base classes on how to deal with scenarios. So Magpie is really just 1,600 lines of code. It provides a number of models. It provides way to take a file and model it as an array of lines. As an IST through XML, it provides ways to model configurations. It provides a native way to deal with Python IST with Astor. And all of these models is something like 1,300 lines of code. So that's to take one part of the software and model it. And that includes all the transformation you can do. Yeah.
I missed Astor. What was that?
So Astor, so question is, what is Astor? Astor is a native way to get a Python IST. I will go later on the models Magpie provide. So you can see later if it's clearer or not. It's basically a way to directly manipulate Python IST inside Magpie. It's not really that useful now. It came back from the days of Piggy, but it still exists and it's still part of the of Magpie. So Magpie provides algorithms. It provides many different local searches, variants of genetic programming, validation algorithms, ablation analysis, 800 lines of code for all of what algorithms are. It provides many ways to compute fitness based on time, repair, blot, output, on a few entry points. And if you don't really are in the know for Python, it includes one file which is _main. And it is important because that will allow you to simply use Python Magpie rather than to actually, that's a weird way that Python used to execute subfile. So this one, yeah, the _main is the one file that you want to execute. And there is also an increasing number of tests. So every time I find a bug or every time I develop a new feature, I'll try to increase that number of tests so that, yeah, we do not have too many bugs. So the philosophy of Magpie is everything is self-contained in the Magpie folder. So the one that contains _main. You can either take that folder and put it alongside your software, or take your software and put it inside the overlaying Magpie one, so the one you clone from GitHub. And you need basically to have on the one side the Magpie folder, on the other hand your own software. You need to provide a scenario, and then you will be able to do stuff like Python 3, Magpie, local search, -- scenario.txt. And then Magpie will go on by automatically generate a folder which is Magpie work. It will clone your software, try to apply transformation, run it, and it will generate Magpie logs, which will be basically the log of everything you've done, the final patch, the final diff, and those are automatically generated. So yeah, you don't need to install anything. You either need to copy your software along beside the main Magpie repository, main Magpie directory, or you can simply just take the Magpie directory and put it alongside your software. Both will work. And the intended way to use Magpie is simply to execute the Magpie folder. So Python 3 Magpie, that will automatically run the _main by specifying what you want to do. So Python 3 Magpie local search or Python 3 Magpie minify patch, and you will need to provide the scenario file and, for example, the patch. And we will do that together in the next part of the tutorial. The scenario file, it's simply an ini configuration file. You will need to specify where your software is. So in this example, the software is in the example directory. It's example /triangle Ruby. You want to target a single file, which is triangle.rb. We want to repair a bug, and there is two commands. One which is I want to execute bash on one specific shell script, and to test whether or not the bug is fixed, you can run Ruby test triangle. So that are the commands that Magpie will automate alongside applying transformation. And for the search, we want to do a search of 100 steps. We want to do line replacement, line insertion, line deletion, and we want to stop as soon as the number of bugs goes to 0. So this is copy-paste of one of the scenario. And if you have your Triangle Ruby software, you can write this, give it to Magpie, and it will apply 3 types of transformation until it is able to run Ruby test triangle and get a number of bugs which is 0. So as you just seen, you need to give to Magpie to provide the commands that it will automate. There are 5 commands that you can provide: init, setup, compile, test, and run, 2 of which will be applied at the very start of the search, init and setup, and 3 are executed once for every variant that Magpie will evaluate. So init and setup is basically the same thing when it's done even before Magpie starts, and we will see example of why that might be interesting. And setup is basically for pre-processing, and we will also see examples of when this can be interesting to do. So basically, the main example would be to pre-compile your software. So then when you apply your transformation, you only recompile the part that has changed and do not recompile everything from scratch. In that scenario, you may want to compile before the search once so that you don't spend too much time recompiling everything every time. So just to save resources. And for compile, test, and run, compile and test are basically the same thing. Compile is for test and run preparation, and usually used for compilation. You want to run GCC, for example. And then test and run. Test is used more for a semantic test. So you may want, for example, to run your test suite and verify that it still passed your test suite. You did not introduce or transformations that introduce bugs. And then run is the one for which the computation, fitness computation is performed. And for all of these 3, or all of these 5, then you can get a result which can be a failure. So you have generated something which is not interesting, or if it passes everything, you will get a fitness value, and that will be used to see whether you want to keep on that path or not. You do not have to specify all 5. So here we just specify 2, init and test. You need to specify at least once, because otherwise it won't do anything. But there are leeway on what you can provide, and there are that many steps. There are 5 steps, so that also in the log file, Magpie will be able to describe you with precision what failed at which part of the pipeline did it fail. So on the components that Magpie provide, it provides 3 types of models. One which is based on a list, which is simply you take the file, you split at new lines, and that's your list of lines. And you can do line replacements on that model. You can insert lines or delete line. It provides 3 types of model which are based on trees. So XML model is you start from an XML file, and we will see that, for example, SourceML is a tool that is able to start from a source code file and is able to output the IST of that file in an XML format. So the XML model does that. It takes an XML file and it does transformation on the XML tree. It can do node replacement, node insertion, node deletion in that tree. And for a specific node, it can change the text of that node. For example, changing a number for another number. And it can do wrapping. For example, it can take a number, or it can take a variable and wrap it with a parenthesis on +1 on a parenthesis. So you can replace any x in your program by x + 1. So it's something that it is able to do. SourceML model is the exact same, but in the way that SourceML is a tool that is able to take a source code file and output an XML file, SourceML assumes that you want not to have a modified XML file, but you want to have the underlying source code file on which was computed the XML. So instead of doing transformation from XML to XML, it will do the transformation from XML to XML, and then it will give you the source code file. So for the previous question, Astor is a model that takes a Python file and that use Python native libraries to compute the source, the IST. And from the initial, I think, Piggy software, it is able to do statement replacement, insertion, deletion. So in the Python IST of a Python file natively. So without using sourceML, if you have a Python file, it is able to get the AST, do the transformation, and get you the new Python file. And finally, for the third type of structure, there is one model which is dictionary based, and it is used for algorithm configuration, for which you have a list of parameters and a list of value. So it's dictionary based if you speak Python. It is hash map based if you have more if you prefer the terminology which is more computer science. So hash map or dictionary, basically a key value structure. And Magpie will automatically find the right model to use based on the file extension. So if you have .params, it will assume that it is a parameter file. If you have a .xml, it will say, hey, it's an XML file and I want to do XML transformations. You can associate what you want, but by default, it will do that automatically for you. And yeah, again, for all of that models, it's basically 1,300 lines of code. So model and transformation. If you want to write a new model, it means that it should be quite a short file to write. So it should be quite easy to extend. For the algorithms, there are many algorithms in 800 lines of code based on local search, based on genetic programming, some that are only used for validation, and a few others. In red are the ones that are really interesting. First improvement for local search, one of the variants of genetic programming that work. But for one of your previous papers, there wasn't much variation in the expectation for all the genetic programming variants. Basically does the same thing. But this one in red is both simple and effective. Validation based. So if you already have a patch, valid minify will take that patch and try to remove the edits that are not interesting. So you can have a smaller patch for the same improvements. Valid test is if you have a patch and you want to revalidate, it will just take that patch and evaluate it. Valid single is something that I found out a few days ago that I implemented twice in the 800 line of code. It's not really used. It might be useful. It just take one patch and evaluate all the edits independently so that you can give it a list of edits and see how they fare individually. And ablation analysis will take one patch and will try to describe to you which part of it is the most effective and which part of it is not really that great. So it will be able to take a sequence of edit and tells you these three ones are really what makes your patch effective, and all the others are basically just noise. So it will be able to explain that to you. And yeah, it does have random search and random walk if you do research. If you just want to improve software, it will not be that interesting for you. If you do research, it's a nice baseline to have. Finally, on the components that Magpie provides in terms of fitness, it does provide you fitness in terms of execution time, program repair, and bloat or output. It will basically compute that for every variant that it evaluates. Time is the most simple one on the ones that are used in basically all examples, which the one I don't recommend, it's the native stopwatch of Python. So it will work every time. That is what I use it in the example, but it's not the best one. It is noisy and not really that great, but it works every time. So that's what I use in the example. It provides way to use POSIX, perf, GNU time, with stuff that it will read on the standard output or standard error. For program repair, it will try to automatically read the output of GUnit, PyTest, Minitest to count the number of bugs, count the number of tests. I just finishing that. Blot is just a way to compute the program size, the software size. So if you do transformation and it still pass your test suite, but it's smaller, that's something that you may want to look at. And output, if you are optimizing your own software and you are able to write yourself somewhere in the output, Magpie fitness and a value, it will simply use the value that you provide.
I just want to ask about what is the difference between, like, what would you say to be a difference between like odd time, there's like time, oxy time, and perf time? What would you say to be like the differences and like the advantage of like using one over another?
Yeah, so I will have a slide for that in the tutorial itself. So the question is the difference between all of the times. So the first time is simply a stopwatch in Python. I start a stopwatch, I execute the command, and I stop the stopwatch. It works. It's native in Python. It will give you an execution time, but it will be very noisy. POSIX time is if you have something which is POSIX compatible. So if you have user bin time with POSIX, it will write in your standard output real, sometime user, sometimes system, and sometime. And it will look at that and take the value that is after the word real in standard output, in standard error. And perf time do the same, but perf is way more precise. I think POSIX time is to the hundredth of a second. So you can have 0.01 second, but not more. Perf is way more precise. And yeah, it will read 3 points, blah, 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 seconds time elapsed. So Magpie will look at that. Perf instructions that if you have access to hardware counter, then somewhere in the standard error, it will be able to take the right value. And GNU time, perf time, which is new this year, you can just write in your scenario file some part of the output on the standard error, and it will take the value that is the closest to that part. So if you use, again, I have that in a later slide, if you use perf on within angle brackets instruction, it will look at the line in the standard error that contains the instruction, and it will take the value that is just before or after. So that you don't have to implement 10 different fitness for perf. If you want 10 different counter, you can just write in one line in the scenario file. I say nicely, this one is the last. And that's a different way Magpie can be used. So the recommended way is simply Python 3, then Magpie, then the things that you want to do. So for example, Python 3, Magpie local search, Python 3, Magpie genetic programming. But it also accepts Python 3, Magpie bin / local search .python. If you, for example, want to autocomplete, that is something that works. Because the native way to do that in Python is to use the module argument in Python. So it should be Python 3 -m magpie .bin .local search without the .py and with slashes replaced with dots. I don't like it. I think it's way better to say, just write Python 3 Magpie local search and it will work. Or if you want to autocomplete, okay, Python 3 Magpie bin, and then you autocomplete local search. It will work. But yeah, no, explaining that you need to replace slashes with dots, that you need to, it's complex. And then, so Magpie will provide two types of search, local search and native programming. It provides one utility to show you all the different locations and provide utility to show you the patch. So if you have a patch in Magpie format, it will compute the diff. You can revalidate one patch that could give you. It can take one patch and try to make it smaller. It can try to explain you one patch and some script to deal with XML. how to take one XML file and to get the source code back. One to take a file and have an AST representation in XML of simply line by line. And as an alternative to SourceML, which supports C, C++, C# and Java, we have Python to XML to take a Python file and have an XML file with the AST. And for those who are using Magpie, the things that I had since last year, I did support for multi-objective optimization. So if you want to have to optimize multiple things at the same time, you should be able to do it now. The algorithms are still single objective, so there are still work to do in that direction, but the basis for multi-objective optimization is done. Support for maximization, if you want, you can improve minus time, and it will, so you can, for example, say, my fitness is time, and it will try to minimize time. We still passing the test suite, and you can say, I want to minimize minus time, and it will try to generate variants that takes more and more time, still passing the test suite. So yeah, that's the same thing as multi-objective optimization that works. And I introduced templated fitness function on edit, so you don't have to write Python code to have a new fitness function, for example, for perf or for types of replacement for XML. Before that, you needed to write them in a Python code to give it to Magpie. Now you can simply write that in your scenario file. You can just say, I want XML node replacement of a statement, and it will take your XML file and replace one statement by another statement. Yeah, so that's much easier to write in terms of scenario files. Things that I changed is now fitness function as now first-class citizen. Before that, it was kind of hard to introduce new ones. Now it should be much easier. Yeah. A few things changed for consistency, and a few bugs have been fixed. And now for the part that should be slightly more interactive, if you want, is the part in which we can use Magpie yourselves. So if you want to follow along, you can simply clone the repository and go for it. The first scenario that we look at is this one, is the one that you can find when you clone it on the README. So if you want to follow along, you can start there. And I will try to do that. So the first scenario that we want to consider is that will be example triangle C Magpie scenario slow. That will take the triangle C software. So in example triangle C, and we will want to improve one file, which is trianglec.xml. Okay, so it skipped one slide. So the first scenario that we want to improve is Magpie example triangle C on scenario slow.txt. And on that example, we have the triangle C software. We have triangle.c, triangle.h for the headers, run triangle for the benchmark, test triangle for the test suite, a Makefile to compile the C software. And we provide one init slow, which is basically to seed the bug, because triangle C does not have a bug. We will introduce one bug, and an XML file so that you can run the example without have SourceML installed. So the scenario is simply, where is the triangle C software in the example folder? Which file we want to improve? Triangle.c.xml, we will improve time, and we will use 4 commands. One which is bash init slow, so that we can introduce the bug. I will show you that file. And to compile, we'll just call make to make test, so the test suite and the benchmark. And the test command will be running the test suite. The run command will be running the benchmark. And we will look at the time to execute run triangle. If we can run run triangle faster, we are happy. If we are running run triangle slower, we are not happy. And we will have, three different transformation. We will delete statements. We will replace a statement by another statement, and we will insert a statement anywhere in a block of statement. Preparation is basically just so that it's easier for the example. In the technical side, we will just patch the code on the header to add one fault. And the patch we will apply is simply adding a call to delay. And we would like to run sourceML on triangle C to get the XML file, so the IST. Instead, we pre-computed it, so we already have the XML file. So what we want to do, what we could have wanted to do is we want to improve triangle.c through the XML. So before running Magpie, we will automatically run sourceML. Instead, because I don't expect to have sourceML installed, we already pre-computed for you triangle slow.c.xml. It will just put that at the right place. There is no setup. If we look at a different example, triangle.-cpp, this one use, so the C++ one use CMake. CMake has a dedicated build folder. So the thing that you do not want to do every time, and you want to do only once at the very beginning of the search, is to create that build directory, to go to inside it, and to run cmake ... so that it can do the initial stuff it wants to do inside the build directory. So that's something that you do not want to spend time doing for every variant. So you can just tell Magpie, do it once at the beginning of the search, so that it will automatically reuse it and not spend time running cmake ... for every variant. So the bug is we introduce one function, which is just spend time on one call to that function. And for what is the representation? So that's one fragment of the code. It takes two values and sort them around. If you take that fragment and look at the IST in XML form, you can see that sourceML will insert tags for comments for each statement, and if where is the condition, where is the expression statement, which is in fact a statement, which is a name, an operator, blah, 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 blah. So that's what sourceML is able to generate. So that's what, I have 30 slides more. So. Yeah, I will probably just keep that. So let's run Magpie. So as I said, you should be able to just say Python or Python 3. We want to execute Magpie, and we will just do local search the scenario, which will be example triangle C, and then the scenario file, scenario slow. So this one. Local search. And then Magpie will execute. So that's something that you can, without the colors. Yep. Sorry. Let's go ahead. Now we're back. So the first thing Magpie will do is evaluate the original software without any transformation. It will do that by default 3 times to get reference fitness, the thing that you want to beat, and you want to be faster than 0.08 seconds. Yeah.
So the line saying red, that's just information. It's not actually running.
Yeah. No, by default, it takes the last one. So there are three fitness evaluation, and the reference by default is the last one. So it's a copy of the previous one. It's not very interesting, 0.08, but we are just looking at output. If you are more interested in the value themselves, you will have the true value in the log file. But if you are just looking at is stuff happening, you don't need to have something, too much information in your standard output. It will be in the log file. It will then start to run the local search because we started the local search. We will see that it's generating variance at different level of success with or without fitness values, and it will give you some more information. In the log file, there will be much more information. For example, this one failed to run the test suite. The 2, 3, 4, 5 did have a fitness value. Two that are slightly faster, one which is slightly slower, one which is slightly faster. These two failed to run the test suite. So you will have that in your output.
When it says test code there,
Yeah.
that might mean that it failed.
No.
Ah,
So that it tried to run the command for test on this one as an error. So that's why the pipeline is 5 steps long, so that it will be able to tell you it failed to compile or it failed to run the test suite. And yeah, every time it finds a new base value, it will also tell you, for example, here it's in green. This one is 3% faster. This one is 93% faster. So in the output, you will be able to see in red what failed, in green what is the best. The runs that are cached, so not evaluated again, but simply taken from the cache. So we have 5 steps. Every step you can have issues. For example, it failed to run the command. The command did not, the command crashed. The command took too long. The command generated too much output, or we weren't able to find the fitness function in the output. And if everything goes fine, we have success on a fitness value. You can specify for each of the steps the command, the timeout, the size for the output. And if you are running things multiple times, so for example, for batch processing, you can also tell you that you want the entire runs not to take more than a threshold for time. So you can say, if you run, for example, minisat 5 times, you can say, I do not want each minisat run to take more than 10 seconds. And I do not want the whole 5 repetition to take more than 30 seconds. You can do that. And if anything fails for the initial software without any transformation, Magpie will also try to self-diagnostic and tells you, hey, I wasn't able to run tests because for example, it timeout. So look at the command for testing and try to increase the amount of time that is associated to it. At the very end of the search, it will tell you why the algorithm stopped. So for example, here I let it run to completion. So it generated 100 variants. Here I just killed it. So it told me that I interacted with the keyboard. And it will tell you the location of the log file with everything and more. So every edit that it generated, you will have the description of it, and not simply the size. And it will also give you a file for the patch, a file for the diff, and it will show you your patch on your diff. So for example, here, it deleted the call to nanosleep, so it removed the delay entirely, and it had one more insertion that has no impact, but that was probably just there because of the noise of the fitness function. It did the insert, and it was 1% faster because of noise, so it kept the transformation. I don't think I have much time. I have 20 slides more, but we'll simply, don't do the last part. They are not exactly the same tutorial, but in the tutorial files, on GitHub, there will be everything that is in the slides. So just I want to just finish that one part. We won't do the last part of the, well, just want to finish that slide. So for example, here, I got one patch which has 3 edits. It has 1 deletion, 1 replacement, 1 insertion. On the diff, it removes the call to delay. It replaced 1 if with another if. It inserted 1 if at the end. What? So it generated this. And we have, just for convenience, we have the patch and the diff in different files. So if you want to look at them again, you can. And this one is interesting because you can reuse it directly with Magpie. So that's the command that I use to run the local search. I can simply change local search with show patch. I can simply give it the patch. So I can give it the file, patch, and it will simply recompute it. It will remove the diff. I could have also give it the patch directly. It will work also. So I could have done that, giving it the patch, and it will do the same thing, which might be interesting if you want to, for example, say, I want to try that. You can play along and look at it.
So in that case, you manually made the
Yeah.
patch.
Yeah. Or I could have written one edit myself and reevaluate myself. Yeah. But it just recomputes the diff. If I want, for example, to have a fitness value, it's not evaluate, it's reevaluate. Revalidate. I can ask it to revalidate. So it needs a fitness value. It needs a fitness value for it needs to recompute the original one. And then it will be simply one evaluation. So the one I wrote myself with 2 edits instead of 3, it's still 3.45% of the original, 0.00. And very quickly, minify test, minify patch. I can, yeah. So this one is a search that try to decompose the patch to give you the minified one. And it is able to say that, yeah, only this edit is able to find the best fitness, and it just removes that, and it removes the noise. And study it. Perhaps we can stop there with ablation analysis. And this one is able to describe you. So from the 2 edits, it will try to remove them iteratively, and it's able to tells you that with 0 edits, you get 100% of the original fitness because there is no transformation. And then if we add just this one, it goes from 100% to 12%. And if it adds the second patch, it goes from 12% to 5%. So it is able to tell you to do the ablation study of starting with a long patch and tells you which one are the most impactful and the least impactful in the patch. Yeah, I will just quickly go through that. Skip the second part of the tutorial, the second part of the hands-on session, and finish. So, or is it completely, yeah. So it will take 2 minutes to finish? So yeah, you can change the fitness function from time to POSIX time to perf by changing the scenario file and adapting which is a command to run. So if you want to run, for example, perf, you will need to change run triangle to perf stat run triangle so that there is the right elements in your standard error so that Magpie can read that it will not change your command yourself. You can add a seed if you want to repeat things deterministically. It will not remove the noise, but it will be able to fix the order of the generated edit. You can change the warm-up strategy, the number of steps. I will skip the second part because it's the end of the allocated time. But if you go through GitHub, there is a part that is dedicated on Minisat, on in particularly how to do line level evolution for Minisat, IST level evolution for Minisat, parameter tuning for Minisat, on the stuff that goes with parameter tuning, evolving multiple kernel at one time. So for example, how to evolve every parameters for one. Yeah, I'm done. So you can simply tell it the list of transformation you have, and it will just do things in parallel, and finally batch processing. Just one sentence to finish. What I want for Magpie in the future is to make the process more transparent and engaging. There are many stuff that we can improve for a tooling perspective and for a research perspective. I think we will need to increase efficiency, trust, usability, and that's it.